The terminal in programming is a little bit of an interesting thing, because if I just have like a basic hello world program here, right, and I compile this, like it works, right? Obviously everyone knows how to output something into the terminal, right? It's the first thing that you learn how to do when you're programming. But at the same time, it also like can get a lot more advanced than that. For example, this is NeoVim, right? This application right now. It is literally running inside the terminal, right? It's just a generic interface where you can capture user input from like the standard input file, and then you can output using the standard output file, right? Like that's the entire interface. So today I just want to show like how you can kind of capture the full power of the terminal to do whatever you want. And for this example, we're going to do Snake. And today, I think for the first time on this channel, I am actually using Linux. All this stuff is possible to do on Windows. I've done it in an application before. You can look at my code for NeoSkim, my spreadsheet editor, but to be honest, the Linux interface is a lot simpler. And yes, I see all your comments. But what we're going to be doing is using this interface called, I don't know exactly how you're supposed to say it, like term IO, I think. But essentially what it lets us do using this this structure here, right, is you can specify like how different behaviors for how you want your terminal to operate, right? So the first thing I'm going to do is actually just create a bit of a structure for our terminal context here, right? And all that's going to hold now is the original mode that we were in, right? Because we want to, when we initialize the program, basically what we're going to do is tell the terminal to like give us complete control, right? So we don't want to like, normally when you're writing in the terminal, when you type something, it'll like put that output to the terminal as well. We don't want to do that. We don't want to listen to control characters. Like all of that we're going to disable, right? So, but obviously we need to restore that at the end, hence the original thing in our terminal context, right? So I'm going to call this one term create, and then for now this is just going to be void, and then I'm going to create another one called term quit, and then that is going to take in one of our context variables. Okay, so first thing we got to do in our create function here is to call this tc get adder function, right? So what that's going to do is if we're given, well, actually first thing I'm going to do is create our term here. We're going very against my normal grain today. I'm going to be using malloc and free just because this is a relatively simple program, but as you know, I prefer arena allocators. So first thing we're going to call is this tc get adder function, right? And what this just does, it takes in like your file number, right? So we're just using standard in, and it will return what the current settings are for the terminal, basically, right? And then I'm going to create a new variable here, I'll call it raw, and this will just, we're going to edit our terminal settings to basically turn off all the stuff we don't want. And honestly, there's a lot of stuff to go through, and I don't fully understand all of it, but there's this excellent series about how you can create a text editor in the terminal here. I'll link this below. And just in this part of the series, right here, it has pretty much all of the stuff that you could need. So I'm literally just going to copy that, right, and format it. So the one thing here, let me close this real quick. So you can see most of what this is doing is just like disabling certain flags and all of this stuff. And you can look at the man page to see like what each of these things do. But like some of the stuff is like like the echo and canonical, like disabling, like I said, when you type into the terminal, like normally it outputs what you're typing. This stuff, these two flags down here, this allows the terminal to, when you're reading input, right? So vmin says like still return read if there's no characters, like obviously it would normally block. And then time, this would is like the a max timeout, right? I'm just setting that to 0 to like process it as fast as possible. And then we're going to call this set adder function, right? So still on stood in file now. And then I think this actually takes in, oh, it does take in an action. It's like tca flush, I believe. And then we're going to pass in our new pointer, and we're going to pass in our new thing there. And obviously, in a real program, you should be like checking the output for all these variables, but I'm relatively confident that this is going to work. And then so here in our quit function, it's the same thing, except instead of our raw terminal IO, we're going to pass in that original one, right? And that's just in our context. All right, and then we'll also free the term. Okay, so this is the basics, right? If we now create our terminal context, I'll also call the corresponding term quit, and then I'm just going to make an infinite loop here, and we'll say our input is just some variable here, and I'm going to say read from std_in to our input, just one, right? And then obviously do want to have some sort of quick condition, so I'm going to say q, and then literally what I'm going to do here is I'll print the like integer value of the character and then the character itself. And then I think, at least on Linux, you do have to do the carriage return to make the new lines work properly. And then this is just going to be input, right? So what you'll see is that here we'll say if input does not equal 0. There you can see the fact that we are getting a lot of the 0 inputs, right? Because nothing is happening. Alright, so now when I press a key, it doesn't actually press that key, but it will still give this that information, right? And the cool thing here is, even if you do, like here, I'm going to press an arrow key, right? This will give you, this is actually an ANSI escape code sequence, right? But it still just gives you all the information, right? And you can even do some crazy stuff, like that's a control arrow key, or you can do, sometimes the function keys will do stuff, yeah. It can get a little crazy, but for now, honestly, for the snake game that we're making, I'm just going to use WASD because that's more easy to process. But what I'll do in a real application is have some sort of layer on top of that that can like filter in the input you're getting, right? So it'll like consume multiple characters if you have an arrow key, for example, and then convert that to some sort of internal structure. But the other thing that I'm going to do here is, because we're going to be writing to the terminal a lot, is that I actually just want to have some way to like block and group together all of those writes. So in our terminal context here, I'm just going to create a little buffer that will store like our writes to the terminal, right? And the other thing that I do want to note here is that the way that we're setting this up is that, and I'll give it like a megabyte of capacity. All of this stuff is relatively like operating system agnostic in a way, as long as your operating system supports like, or your terminal emulator supports those ANSI escape codes, which now even on Windows 11 it does. Like I believe that's the preferred method. So like this section of the structure you can just kind of output into, or like you can isolate it into some sort of operating system specific layer, and then the rest of this will be like common between all the operating systems. Again, you can take a look at my code for the spreadsheet editor, but for now we're going to do, first off, I'm going to have a function called term read because this is OS dependent, and this just will do we'll say, yeah, I'll call it keys, and then capacity, so like the maximum we can read, and it'll return the number of keys that it has read. And then we're also going to have a function to write to the terminal. And for this, I'm just going to spin up a quick length-based string. You can see my video about that if you're interested. So size, make that U64. And then I'm also going to do a quick macro to have literal strings. This is, again, just standard stuff, but if you want to dive into that a bit more, you can feel free to watch my video on it. Alright, that should do it. And then, okay, so in our write function, that'll take a string to write, and then I'm also going to add a quick helper to just write a single character, and then also have a flush function. So this is the function that will actually do the literal operating system write call, which again is operating system dependent. Okay, so first off, in our create function here, this now takes a capacity that I did not spell correctly, and then what I'm going to do after we get into raw mode here, we're going to say our buff capacity is equal to capacity, and then our buff size is equal to 0, and our buffer itself is just the malloc of the capacity. And then just to be kind of on the safe side, I am going to zero out our buffer, which will be size capacity. All right, so now for read, again, this is why I chose to do the Linux version here and not the Windows, because the Windows is a little insane. We're literally just going to return read of stdin, and then like literally just one-to-one. And then for write here, I believe, well, so what we're going to do actually is we're going to say that while the string size is greater than 0, basically we can only print in chunks of like the capacity that we have left to write, because of how we've set this up, where we're writing to the terminal buffer and then writing to the actual file. So I'm going to say to write here, and I'll call this will be the minimum. So the most that we can write at any time is the capacity minus the current size, right? And then the maximum that we can write is the string.size. So I'll mem copy to the buffer at its current position, the strings buffer, and then we'll say to write, and then I'm going to increase the buffer size by to write, and then decrease the string by to write. So that means incrementing the pointer of the string and then decrementing the size. And then if our terminal buff size is greater than or equal to our capacity, then we need to not use square brackets, but we need to call this term flush function, right? And again, that's the function that actually does the write. And then again here, this is basically the same thing. We're going to say terminal buff at buffer size is equal to our character, and then if our, honestly, this is the exact same if statement. So I'm just going to copy that. And then in our actual flush function, this is just going to say write, so sit out. And again, you should probably do some sort of checking on that return value. I do not have time today. All right, that should do it. So now we have the system. So we're able to create the terminal. It'll create it in this like raw mode where we're able to process the raw inputs and write directly to it, right? And then we're able to write to this buffer so that we can batch our writes and ideally make it a little faster, right? And now the other thing that I am going to do here is, so, well, first off, I should mention, now that we have this set up, the primary thing we're going to be using to control all this stuff are called ANSI escape sequences, right? Hopefully this is big enough. But the first thing, really quickly, that I'll do, which I believe is best practice when you are taking control of the whole terminal, which we're going to do today, is use this alternate buffer. So when we initially open the terminal context, I'm going to enable the alternate buffer, right? And here I'm going to do that by saying, actually we'll just say, I'm going to say to write. I'll make a little string here so it's easier to get the size. And that's going to be, so the escape code, which is in hex, that's 1B. And then it seems like it's open square bracket, question mark, 1049H, like so. And then the other thing I'm actually going to do for the initial is to clear the screen, which I believe is 2J, right? So all the ANSI escape sequences, I believe, start with the escape and then this open square bracket. And then, so here, I'm going to write this one directly. And this should actually go to sit out. Like so. And then when we quit, I'm going to, here, instead of doing H to enable the alternate buffer, I believe it is L to disable it. And that should do it. So now we'll go into draw mode, enable this alternate buffer, and we should be good. So a few more things that I am going to do here is, first off, I want to create, what I'm going to do here is have some sort of structure that is I don't know if window is the best term. I'm going to call it window for now. But it's basically a tile on like an internal buffer representation of our screen, if that makes sense, right? So that'll be some sort of character, in this case just ASCII, and then also some sort of color information. So for that, I'm actually making another structure here, and this will be a color for the window, and that's just RGB, like so. So we're gonna have an FG color foreground, and then a BG color for background, and then a win buffer here is just going to be some sort of width and height, and then a list of these wind tiles, right? And the goal is that, well, this accomplishes a few things. First off, it just makes it a little simpler from like a user code perspective to write to this buffer directly instead of writing to the console directly. And it also, you can also do some fancy things. Like in my spreadsheet app, I actually have 2 buffers. I'm like double buffering, and then I only draw the differences between the current frame and the last frame. You can even do like, you can get the size of the terminal each frame, so like dynamically resize your buffer. But honestly, right now, because we're just doing simple snake, I'm going to hard code in a width and height, and I'm going to make that 16. So now what we need to do, so we've got the terminal created, and then I'm going to create a wind buff, and I'll call this our window. And the width is just going to be that width we defined. Our height is our height, and then our tiles is, again, we're just going to malloc size of wind tile times width times height, like so. And I cannot spell. All right, so that's the window. And then what I'm going to do, okay, so we're going to have some sort of update here, will happen later, and then some sort of draw. And first is I'm going to essentially clear our entire window, right? So that's going to be through width and height. And I'm going to just set the data tile, the color to, or the character, not the color, to be a dot. I'm going to have that represent like kind of the background of the screen. And then the foreground color will be just white. So that's 255. And then our background color is black, so 000. All right, so that'll clear the thing. And then, well, first off, so before we get to anything more complicated than that, I'm going to do the actual drawing here. So again, like I said, if you want to do something slightly more performant, you could do a thing where you like only draw the differences between like frames that you're drawing. But honestly, in our case, this is going to be fine. So first thing I'm going to do is that 2J command from earlier, which will clear the screen. And then the other thing I'm going to do is this H command here, which controls the cursor position, I believe. So yeah, right here. So that moves the cursor to like the top left of the terminal, right? And that's where we want to be when we're going to start drawing. And then I'm going to loop through, because we're drawing rows, I'm going to loop through Y in the outer loop, and then X in the inner loop. And then, so here what we're going to do, I'm going to handle color in a second, but the main thing is just to write the character that we're at, right? And the index is X here. We'll say, I'll call index, I'll pull this out here. And this is just standard, like, indexing a 2D array. So that index, and then there's the character. And then that'll automatically like increment the X, right? If you're drawing the difference, you'd have to do some cursor positioning commands as well. And then we're gonna write another code, and I believe this one is E, or maybe it's 1E. And that should, yeah, right here. It'll move the cursor to the beginning of the next line and one line down in our case, right? So that's like we're wrapping down, right? So if we just run that right now, we should see, oh, that's actually going quite fast. So the first thing we want to do that I forgot about is to flush the terminal at the end. And then I'm also just going to call uSleep, and I'm going to give it a good 200 milliseconds right now. And that'll be like our game loop, quote unquote. Obviously for Snake, that does not need to be very quick. And then, okay, so what I'm actually going to do is I want to make a few helper functions here. So the first thing I'm going to do is have a Boolean that checks if 2 colors are equal. So I'll take in a color A and a color B. And then I'm also going to have a function here to set the color of the terminal. I don't know. These are not the best function names, but it does not matter right now. And then I'm going to have, so just a quick Boolean to like, if it's true, it'll set the foreground color. If it's false, it'll set the background color. So coming down here, so our color equal, that just return a.r equals b.r, a.green equals b.green, a.blue equals b.blue. Very exciting stuff. And then for the actual color here, we're going to be using slightly more modern terminal feature. You could go with like slightly different things, like there's some built-in colors, there's even like these 256 color palette, but we're going to do the 24-bit RGB color here, right? So it's these two escape sequences that we're going to be doing. And honestly, for this, I am just going to use SNPrintf. So the first thing I'll do is I want to get the size. So here, let me just say we're going to have some string here, right? That's going to be equal to our escape code, and then either 38 or 48, and then 2, and then 3 characters for red, or up to 3 characters for red, 3 characters for green, and then up to 3 characters for blue, and then M, right? So this is our string, and like as my language server says, that's 20 bytes right now. So what I'm actually going to do is just create 20 bytes for our characters, and actually I should probably do 21 because I'm not sure if SNPrintf adds null terminators, but I do not want to take my chance. So we're going to pass in our characters and then size of chars, right? And then our format for this is going to be basically what we have here. But obviously instead of these underscores, I'm going to add %ds. And then, so for the first one, it's 38 if it's a foreground, 48 if it's a background. So I'm going to do a quick ternary like that. And then just red, green, blue, like so. And then we're also going to grab the size output from that. And then I'm going to call term right. And the string that we have here is our characters, and then just the size. And that should do it for setting the color. So if I just do a quick here, if I say terms, or if I say set call, and we can do like a, should be like a turquoise that's all blue, all green, and I'll set the foreground. Actually, you know, I'll set the background. Should be a little more exciting. Boom! Wow, that, oh, it is late and that is hurting my eyes. Okay, but that works, right? So what we can do is we can set the color to the first color that we have, like the top left, and then check if a color has changed between now and the last character that we've written. So for that, we're gonna need a prev foreground color and a previous background color, and then we're going to say if our colors are not equal, if the previous foreground is not equal to our current foreground, then first off we need to set that color to the actual terminal, and that's 1 or true for the foreground. And then we need to update our previous to be whatever we have here, right? And then same thing here, just replace FG with BG. And I did not do that right. All right, so now this works. So like this is pretty much it in terms of like how you can write to the terminal. It's just with liberal use of all of these ANSI escape codes, and you can take a gander here at all this stuff that we have. There's really a lot of stuff you can do, especially if you're making, like, this is kind of a more general structure that I'm doing here where we're writing to this buffer. But if you have like a more streamlined application that you can get it done with less, you know, go for it, feel free. So now that we have this, I'm actually going to start making our snake stuff. So first thing I'm going to do here is just create a quick vector2 struct, and then we're going to have our snake is just going to be like a list of these vector2s. And honestly, I'm not going to bother freeing all of these mallocs that we're doing at the front here, because like they're going to last the lifetime of the application, so I do not care. Snake size. Oh, and then we also need some sort of direction system. So I'm going to make a quick enum. So we're going to have up, down, left, and right. and I'll just call that dir, and then we'll have which is going to start off with right, and then I'm also going to say the snake size is 1, and then our initial snake is at I'll do like width over 10, so like closer to the left side of the screen, and then height over 2 in the middle. And then we also need the apple, so I'm going to say I'll initialize our random number generator, which again, if you've seen my previous videos, you know I don't love that, but for today it does not matter at all. So now we have our vec2 for apple, and that's equal to rand modulated by our width and our height, like so. So when we actually go to draw it here, what I'm going to draw the apple first, then the snake. So we're just going to set, here I'll grab an apple index. Actually what I can do is just say win.data at apple.x plus apple.y times the width. I mean, I should really be saying win.width because that technically might change. And then we're going to make that a tile where the character is A and the foreground color is all red and the background color is just black. And that should do it. Okay, so that'll draw the apple, right? Just setting that tile on the screen. And then we're going to say for I in snake size, take our win.data at snake, here, we'll say, I'll call this segment, and that's just going to be the snake at I, and the data at segment.x plus y times width equals a tile where the character is, I'll make this like a hashtag because that's like one of the most solid characters, and then green, and then the background color is also just going to be all black, like so. Okay, so that should draw the snake, and if we see, we should see that we got, yeah, perfect. So we got an apple rendering, and that's all red, and then we've got the green hashtag for the snake here, right? So that all appears to be working. So now what we have to do is actually update the snake. And honestly, I think there's like a million ways you could do this. You do not need to be, excuse me. Like you do not need the actual implementation here does not matter. I just want to have some sort of proof of concept for the way that this terminal system could work. So the first thing I'm going to do is switch on the input itself, and that can change the snake direction. And actually one of the cool side effects of handling it in the terminal like we're doing it now is that it'll actually, like, because we're just reading from, like, we're incrementally reading from standard in, this will automatically kind of buffer your input. So I don't know if you've ever made a snake clone before, like it's best practice to keep track of all their inputs. Like if the user presses like right then down really quickly, you want to process both of those, and this, as just the side effect, automatically does that. Although actually what I'm going to do here is I'm going to grab the head itself, and then we're going to update that, and depending on whether or not, if the head has landed in the apple, then we'll update the rest of the body, and you'll see how that works in a second. So if we're going up, then we're going to have the head.y minus, and then if we're going down, that will be plus, and then these are both going to be x, that will be plus. So if we're going left, decrease x, if we're going right, increase x. All right, don't need that. So first thing is just if the head is outside of the bounds, right? So if it's greater than if it's less than 0, greater than width. If the y is less than 0, y is greater than height, then just break. And then the other thing, first off, what I am going to do is actually, I'll have another function here that'll just check if a point is in the snake. So that'll take the snake and the snake size, and then also a pause to check, like so. And then, I mean, this is just really simple stuff at this point. We're going to loop through the snake. And then if the snake at x is equal to pos.x and snake.y is equal to pos.y, then return false. Or actually, no, return true then, because we are in the snake, and then return false out here because we loop through every segment and not hit it. And then, all right, so now back in the update. So if our head is outside of the bounds, we've left the bounds, then we're going to break. If we're in the snake, then we are also going to break. So those are like the two lose conditions. Honestly, when you're handling input here, you should probably check to make sure that you're not doing like a 180, because then you just instantly lose, but it doesn't really matter. So that'll do that. And then what we're going to do is check that if our head is equal to our apple, then what we're going to do is first off, create a new apple position, right? And I'm going to use a do while for that. So the apple.x is equal to rand mod width, and apple.y is equal to rand mod height. And we're going to do that while it is in the snake, the apple is, or it is equal to the head, right? Honestly, I'm just going to copy that. So that'll ensure that our apple does not intersect with the snake. And I'm not checking for a win condition here. To be honest, it'll just loop infinitely. So I guess you've won the ability to go into Task Manager if you beat it this version. And then, all right, so now we've eaten the apple. So what we want to do is say that our snake size, we'll increase our snake size and then set the last one to this new head. And then else what we're going to do is say for I less than snake size -1. Again, I don't think this is the most performed version of snake, but I don't think you can program it in a way stupid enough to where the performance actually matters in this case. So I'm just looping through the whole list and incrementing it, and then setting the last one to the head there. And I think that should do it. Here, let me check. Let's see what we're working with. Alright, so if I use the arrow keys, moving around, and I totally missed that. Now, one side effect of using the terminal for this specifically is that we're actually, like, you move faster vertically because, like, characters tend to be, more more vertical. Yeah, that's all working. Now I can actually do, I'm just going to play this here. Oh, shoot. So I guess if you wanted like a better version, you could do something where you have like a 2x1, right? So that the characters are like a little wider, but a little more true to life. Yeah, and you can see the buffering going on. It still only reads input every loop iteration. So you could have it, if you wanted, you could do a system where you like read all the inputs available each iteration. But yeah, here, let's check. Yeah. We hit ourselves, it does not work. I'm glad after all this time I still know how to program snake. Yeah. All right, well, have a good night, I guess.